Okay, well, I'm going to go ahead and get started then. So this is Introduction to Cosmology, Lecture 2. And today I'm going to talk about historical astronomy and use that as kind of a vehicle to talk about the scientific method and how we began to understand our place in the universe as a species. So let me just start off by asking a question. How many people in this room think that the Earth is round rather than flat? Okay. Who thinks that the Earth is flat? Okay. So what if I were to say to you, I believe the Earth is flat? Okay. In fact, the universe looks like this. This is pretty much the universe. And the reason that I say this is that, you know, if I go outside and I look around, this is kind of what it looks like. If I look out in the distance, the sky is kind of domed and it looks flat. It looks like a snow globe to me. And that's the universe. So convince me that I'm wrong. Everybody raised their hand and said the Earth is not flat. So how do you know? Yes.
You see the sunset twice. Like the sun goes to the beach, you lay flat on the ground. You see the sun go down the horizon, stand right back up, and you see it happen all over again. So,
oh, okay. So you say, I don't know if I've ever seen this happen, but you say you can see the sunset twice. If you're laying down on the ground at the beach and you look off, you see the sun go down. But then if you stand up, you can see the sun again. And then you can see it go down again. Has anyone else seen that? No one else has seen that? Okay, I don't think I've ever seen that. But anyway, that's an interesting theory. I need more proof, though, because that seems crazy to me that the Earth's not flat. Yes?
If you walk one direction, and let's say if you could keep traveling that one direction, you won't fall off the edge of the planet. You'll end up, eventually, you could end up back where you started.
Okay. You're saying you've never fallen off the Earth. If you keep walking in one direction, you've never hit this end here, and you've gone pretty far. Where's the farthest you've gone?
Ever?
Yeah.
I have been to Europe.
You've been to Europe. Okay, so all the way across the Atlantic Ocean, there's this other continent there. You still haven't fallen off. Okay. That's pretty convincing. So it seems big. Has anyone ever seen a picture of the Earth from space? Okay, that's pretty good evidence that it's not flat. So we have a fair amount of evidence, both from the sort of day-to-day experience of trying to see what the horizon looks like from different heights. I think that's more generally what you're talking about with the sunset. To, look, I've traveled pretty far and I've never hit the edge. It's interesting how quiet the room got, though, when I asked people why they believe the Earth is flat or not flat. I think we take a lot of these things for granted. Now, the Earth being flat, that's pretty easy, okay? It's kind of crazy to think that the Earth is flat, given the fact that we've seen pictures of the Earth from space. Probably some of you have traveled all over the world. And there are other things that you can notice, and I'll talk about them later, about the world around us that betray this idea that the Earth is probably not flat, that it's more spherical. So fine, let's take that. I believe you, okay? You've convinced me that this is wrong. But let me show you something else fine, but this is what the universe looks like then. I'll give you the Earth is roughly a sphere, okay? But how many people believe that the sun goes around the Earth? How many people believe the Earth goes around the sun? Okay? It doesn't look like that to me. So if you get up early enough, you will see the sun rise. As we just talked about, we see the sun set. The sun comes up, it goes over our heads, it goes down. You wait a while, it comes back up again. It seems like it's going around us. The same thing with the stars, right? You look up at the stars at night, the stars are just rotating over our heads. So why do you believe that the Earth goes around the sun? Convince me that the Earth goes around the sun. Any ideas? You can observe the retrograde of Mars.
Yeah.
What do you mean by that?
So like, if you just look at the night sky and you see Mars, like sometimes like you will see Mars like going one direction and then like going back in
Okay.
one direction.
Okay.
And then the zoom is right.
Okay, so he says, well, I've done careful observations of the night sky over the course of months to months to months. And if you watch the planet Mars over the course of a month relative to the stars, it will track in one direction and actually back up a little bit for about a month and then keep going forward again. People call that retrograde motion. Okay? Okay, but what's wrong with that? I mean, I can explain that. So here's Mars. It's going around us. Sometimes it stops and goes back and then keeps going again. How does that convince me that the Earth is that these planets aren't going around the Earth? Any other ideas? Yeah.
We have seasons.
We have seasons, okay.
So
Nice try, that's good. Okay, nice try. Okay. So, I don't fault you for not coming up with anything off the top of your head. All right. This model of the universe right here, give or take, was the accepted model of what the universe was like for the longest period of time we know of in recorded history, something like 1,500 years or more. And a lot of very, very smart people were convinced that this was the right answer. Okay? This was more or less Aristotle's picture of the universe. Aristotle, no dummy. Okay? It's interesting, though, how confident everybody is about believing that the Earth goes around the sun. While at the same time, it's not obvious why you believe that, other than, you know, you've been told that since you were tiny. I have this conversation with my 3-year-old daughter all the time, that the Earth is going around the sun. So she now just, you know, parrots it back to me. It's not clear to me she understands what I'm saying, but so I'm going to talk about this today. I'm going to talk about this progression from going from a picture of the universe that looks like this, which admittedly is very simplistic, to something like this, which is quite sophisticated, but now we know is wrong, to understanding in greater and greater detail about what our place in the universe is and how we fit in. Okay? So most ancient people, as far as we know, and of course this goes well back before recorded history, so we don't know for sure, but it seems like most ancient people, thousands of years ago, most people believed that the universe looked something like this. It was something like a giant snow globe. There was a flat ground canopied by this dome. And that's not a crazy thing to think. That's actually what it looks like. And maybe they thought that the universe mirrored their everyday experience in the sense that maybe they lived in tents or they spent time in tents, and it was sort of like a great tent. Of course, having this view of the universe, it was very difficult to then figure out what the real answer was. It's very difficult to begin exploring what the universe looks like if you kind of take this idea for granted and then keep looking at the ground, more or less. The real adventure in our understanding of what the universe is like began, as far as we can tell, as far as we know historically. The first people to really change these kinds of ideas about thinking about the universe were the so-called Pre-Socratic philosophers. In particular, Thales, who was living at about 600 BCE, is credited with being sort of the father or the grandfather of what you might consider scientific thinking. So he lived in Miletus, which was a port city, an Ionian port city, so in sort of the western part of Turkey there. This guy was a really impressive person. First of all, this was a wealthy city. This was one of the most prosperous Ionian cities. It was a trading port. And so he saw that there were a lot of sort of self-starters, independent people around him. And it's possible that influenced the way he thought about the world. So among the other things that this guy is credited with, so he was basically Pythagoras' teacher. He is credited with 5 fundamental proofs of geometry. He was also a business person. He was wealthy. He became wealthy selling olive oil and trading olive oil in that region. He was an engineer. He was the first person that we know of to divide the year into 4 seasons and to divide the year into 365 days. So he's done fundamental things in astronomy and sort of calendar keeping and that kind of thing. But probably the most important thing, generally, that he did, that Thales did, is he had this crazy idea, this radical notion, that humans could understand how the world works in material terms without appealing to spirits from beyond the physical world. And this is a radical notion at this time. The thing that was unique about what he did and what he did with his students is they attempted to develop explanations for what was going on around them that were logically self-consistent and didn't involve, well, there's some kind of spirit or some kind of God that's making the wind blow. They wanted to know, why does the wind blow in physical terms, and they thought you could figure this out in the basics and those basics. So for example, he thought that earthquakes were caused by waves crashing into the earth. He had this idea that the world was sort of floating on water. The land was floating on water. And actually, he believed in this kind of snow dome, this snow globe universe. And his idea was that there's water thrashing against the earth, and that's what causes earthquakes. Now, this sounds kind of silly, but he wasn't appealing to some kind of, gods being angry at humans and then shaking the earth. And that's what was different. So let me give you some example of some other Ionian philosophers. So Anaximander was probably Thales' most famous student, his best student. And he had a couple of very interesting ideas. So he suggested that thunder came from the shock of clouds ramming into each other. Well, it's not a crazy idea. That's actually not what thunder is caused by, we know. But it's not a crazy idea. I mean, if, why isn't that the answer, right? One of the really interesting things he proposed was that animals, including humans, had evolved from simpler forms. And we recognize this as very similar to the idea that was effectively proven or found evidence for by Charles Darwin 2,000 years later. So that's sort of an impressive idea if you think about someone living that long ago. The important thing here, I give you these 2 examples of an idea that's wrong and an idea that's qualitatively right, to sort of emphasize the point that not all of these ideas were right. But the fact that we know that those ideas are wrong is sort of their brilliance. The fact that they could be proved to be wrong, that they were hypotheses that could be tested, that could be held up to the light of reason, and then dismissed as incorrect once evidence was gathered that showed that they were wrong, is the strength of this kind of thinking. And it's the gem of scientific thinking, because that's what you do in science. You disprove hypotheses. That's all you do. That's all you can do. You can contrast this with supernatural explanations, which you can never disprove, right? You say, well, thunder is caused by gods fighting with each other during a rainstorm. How do you disprove that? Someone would be like, no, it isn't. And you'd be like, prove me wrong. How do you disprove that idea? But if you have a physical hypothesis for what causes thunder, then you can prove it wrong. So therein is sort of the gem, the brilliance of this. Let's flash forward a little bit later, now 450 BCE. Empedocles postulated that there were 4 elements that made up everything: air, earth, fire, and water. So there's earth, the stuff we see, the solid stuff. Fire, you know, you take a log, you light it on fire, it turns into smoke, it turns into air. And then, of course, you know, then there's water. One of the really interesting things he did was he demonstrated that there was something in the air. That the air was made up of something, that it wasn't just nothing. And the way he did this is he used something that's called a water thief. But the principle is very similar to just a straw, right? So have you ever taken a straw, you stick it in your drink, and then you cover up the end of the straw and then hold it up? You trap water in the straw, and then when you take your thumb off, the water comes out, right? You've done that? So what Empedocles said is, well, wait a second now. If the water's not coming out, there must be something pushing back to keep it from falling out. And that something is air. So there's something to the air that can push up against that water and keep it from falling out of the end of the straw, or the water thief that he was using. Sort of like a ladle thing. One of the really interesting people is Democritus, about 50 years later. This was a jolly guy known as the laughing philosopher. He had this idea that there were many worlds that existed throughout the cosmos, that the stars themselves were other suns, and then around those suns were other planets, and on those planets were other life forms. Now this is amazing. So only very recently, you know, within the last sort of 10 years or so, do we have convincing evidence that planets do exist around other stars. Almost all other stars have planets. And of course, we don't know whether or not life exists on them. But this is a pretty interesting idea for someone living 400 years BC. Another thing that he believed was that everything was made of of very, very small things that he called atoms that you can't break apart. So the idea is you start with something, you can keep breaking it in half, but you can't do that forever. And at some point, you break a rock into dust, and you break the dust up into smaller and smaller things. At some point, it becomes something that you can't break anymore, and that's the atom. He thought that everything, including humans, the stuff in space, is all made of atoms. So the reason why I talk to you about some of these things is to emphasize the point that there's no deficiency in human imagination going on 2,500 years ago, right? There were a lot of very smart, very creative people. Many of them had ideas that are commensurate with what we actually think the universe is like today. The thing that they lacked, okay, first is they really lacked the technology to begin testing these ideas in any way. And they also sort of lacked the general scientific method that we've adopted to sort of test and refute hypotheses in a sophisticated way like we do now. But I would argue that mainly it's a technological problem. You know, had these people had telescopes and microscopes and other things like that, they would have made a lot of progress. Because, you know, we're no smarter than they were, for sure. Now, these ideas didn't stick. And so for a long time, this stuff was dismissed. Especially this idea that there were other worlds throughout the cosmos that could not have existed in the mainline thinking a little later on. And the people responsible for basically refuting these ideas were largely, as far as we can tell, Plato and Plato's most famous student, Aristotle. Okay? Plato really hated Democritus's ideas and just trounced them. And if you have a system where you decide whether something's right or wrong by basically making philosophical arguments, without actually devising experiments that test what's right and wrong in a physical way, you can get the wrong answer. Okay? And so, in the end of the day, Plato and Aristotle won those arguments. And there's, they had good reason to win them. Okay, they made convincing arguments, and I'll talk about those now. So let's flash forward a bit. Aristotle, according, at least by written record, is the first person we know about who made convincing arguments that the Earth is indeed spherical. Okay, and this was around 350 BC. Now, the arguments that he made are sort of similar to the ones that we've talked about here, but let me go through them because they're very interesting points to make. Okay, so one of the things that Aristotle realized, and I'm not that surprised that people in this audience didn't really make this argument, because it had to do with what the sky looks like at night. It had to do with the positions of the constellations in the sky. Now, it just so happens that our skies are not that dark. So most of us don't spend a lot of time just sitting outside looking up at the sky. We also have a lot of other things to do at night these days. But people living back then, they had beautiful skies to look at. And they knew what the stars looked like, and they understood the regularity. And Aristotle knew that there were certain constellations that you could see in certain areas of the world that if you traveled to other cities that were far away, especially going north to south, that you could not see any longer. Okay? So the basic idea is the Earth is round, okay, and you're standing here. But if you travel to some distance over here, then your horizon, below which you can't see, is tilted somewhat. Right? So that's the reason why. So if you have a star, if you had some constellation that was here, and let's say you never could see it if you were at this part of the Earth. But if you move to another part of the Earth, then along your horizon you could begin to see that constellation. So he pointed out that as you travel from north to south, there were new constellations that you could see in the southern sky that you could never have seen before. If you're in far southern latitudes, you can't see the Big Dipper, for example. So Aristotle said, that must mean that the surface we're walking on is curved. So the horizon's changing as you walk along it. The other thing that he said was, during a lunar eclipse, okay, and a lunar eclipse is when the Earth gets in the way of the sun and the moon. So it blocks the light from the sun shining on the moon. The shadow that's cast by the Earth is always round. And so the only thing that casts a round shadow, no matter what direction you shine light on it from, is a sphere. So he said it's got to be a sphere. Now notice that part of this argument already assumes what's going on during a lunar eclipse. Right? So Aristotle understood what was happening when the moon got dark and was shaded by the Earth during a lunar eclipse. So this was, again, already a pretty sophisticated understanding of what's going on in the sky. And he used that as one of his arguments for why he knew the Earth had to be a sphere. Does that make sense? So finally, and this is related to, I think, the sunset at the beach idea that we had first. A lot of these people are sailing civilizations, right? And you're familiar with the idea, then, if you're familiar with boats, that if you watch a ship sail off into the horizon, the first thing that tends to disappear the first thing that disappears is the hull, and the last thing that disappears is the tip of the sails. So it's almost like the thing is going down a hill. And it's like you're walking with your friend down a hiking path or something, and they're way ahead of you, and they go down a hill. The last thing you see is their head, and it goes down, right? So again, this was sort of at least three very convincing arguments that it doesn't seem like the Earth is flat, for sure. It definitely seems like it's curved. And add to that this idea that Plato especially loved the sphere, okay? These ancient Greek philosophers just thought the sphere was the most perfect shape. So the idea was then that, well, everything, it's just a natural shape to assume things should be is the sphere. So that's why they went with the sphere. Now, I'm here to tell you that this is just a crazy idea. It is crazy, crazy in accepting the idea that the Earth is a sphere. At least in the standpoint of these people, okay? Imagine you've been told all of your life. In fact, you don't even have to be told. It's obvious that the Earth is flat. Right? In fact, people have done studies. They asked little kids what the universe is like, what the world is like, before they've been corrupted by these ideas that their parents start to tell them. And many of them will say, well, it's basically they will describe something that's flat with a dome. So it's a natural assumption, okay? Aristotle comes along and says, no, 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 there's lots of reasons to figure out that this does not make sense. This is wrong. This is not right. If you think about it carefully, this cannot be the right answer, okay? But there's no intuition from your everyday life that would lead you to believe that the world is a globe. And in fact, there's a lot of things that would make you think this is wrong, okay? So he's telling us that we're like ants living on the surface of a ball. But that's weird, okay? Because ants that live on the bottom of the ball fall off the ball. And ants that live on the top of the ball are easy staying up on the ball. And on the edge, you also want to fall off. But there's no evidence that that's going on Earth, right? No matter what city you're at on Earth, you want to fall this way. Okay, if you're at the South Pole, you don't fall off. So that's weird. So how is this possible? Now remember, they don't know anything about gravity, okay? No one used the word gravity or had a word for gravity or anything like that, right? There's none of that. That was a long, long time later. So how do you understand this? Well, Aristotle had a solution. And his story went like this. The Earth, and all of us, everything on the Earth, is made of material that has a tendency to fall towards the center of the universe. And as a result, the Earth and everything on it is at the center of the universe. And we want to fall towards it. Okay? Now the heavens, the stuff up there, the stars and the planets and the moon, that stuff is made of some unearthly material that's called ether. And the stuff up in the heavens is perfect and unchangeable and uncorruptible. Unlike the stuff on the Earth, which is subject to decay and is chaotic. Things die and rot. The Earth is where things die and rot and decay. The source of chaos. He looked all around him and there were wars going on all the time, right? This is the Earth, with all this messy stuff. But up there in the heavens, everything's perfect. The stars rotate overhead like clockwork. Up there, it's perfect, and down here, it's messed up. Because everything that the Earth is made of this stuff that wants to sink towards the center of the universe, it's fixed, immovable. And it's only the heavens that rotate and move above. So this gave rise to this consistent picture that he had developed, that the Earth is the center of the universe, it's corrupt and subject to decay, while the heavens up above are perfect and incorruptible and unchanging. So a lot of people have this, I think, misinterpretation of this idea that the Earth is the center of the universe, and somehow that means we're perfect and the most important thing in the universe. It was almost the other way around. Aristotle was like, that's where all the junk falls, right? That's where all the bad stuff is, and it's up in the heavens where everything is perfect. So the other thing that this means, right, is Aristotle was well known throughout the literate world. Okay, he was the scientific standard, the scientific authority, and eventually in the Christian world and the Muslim world. So well-read people were aware of this and believed that this is what the universe was like. Literate people believed that the Earth was round, first of all, and they believed it was at the center. So this idea that, you know, Columbus proved somehow that the Earth was round, that people didn't believe that the Earth was round when Columbus is sailing to the Americas is just a myth that was made up. It's not true. People believed the Earth was round. Now, this may seem crazy, but there is an alternative idea that along the lines of what Democritus was talking about, that the other things up in the sky were suns. There was this guy Aristarchus who lived a little while after that, who had this other radical notion that in fact the Earth goes around the sun. Now, why did he think this? I'll talk about his arguments a little bit later because it's really interesting how he was able to deduce this. But he figured out that the sun was much, much, much bigger than the Earth. He was able to use geometry to figure that out. And his basic idea was that, look, it'd be weird for a big thing to go around a small thing. It makes more sense for the small thing to go around the big thing. And so Aristarchus actually proposed this heliocentric universe well before Copernicus. In fact, Copernicus references Aristarchus in one of his drafts of his heliocentric theory. So he was probably influenced somewhat, at least, by the ideas of Aristarchus. But the ideas of Aristarchus were rejected over Aristotle's because they required that the Earth is moving. Okay. Does it feel like the Earth is moving? Okay, that's one reason why people rejected it. Well, that's crazy. Clearly the Earth isn't moving. That's even crazier than the idea that the Earth is a sphere. But there's actually a specific observational reason why Aristotle rejected the possibility that the Earth could be moving. And Aristotle said something like this. He's like, look, let's say I'm walking through the woods. How do I know I'm walking through the woods? How do I know that? Well, I look around and I see all the trees around me. And the trees that are close to me, they move a lot. So I'm pretending you're a tree. If I try to look at you, Mr. Tree, I have to keep turning my head. But the people behind you, the trees behind you, they don't shift as much as you do. So there's sort of a shift in the angle of you relative to the background trees as I move. Okay? To put it another way, if the Earth is going around the sun, okay, here I'm over here, one time a year, and then 6 months later, I'm all the way over here. And I look at things that are nearby. Let's say you're a star, right? On this time of the year, I look at you. Now I have to turn my head this way. And your position relative to people far behind you is shifting a lot. Because when I look at people way in the back of the room, I don't have to move my arm much at all. They're shifting very little. Okay? Or it's like being on a train. You're on a train. The buildings are going by you like this, but the distant mountain peaks aren't moving. So what Aristotle said is, look, if the Earth is going around the sun, then I ought to see the stars' positions relative to each other shift. Like this. The position of a star in the night sky should shift from one time of the year to the next because I'm moving. Because when you're moving and you're looking at something, you have to shift your gaze to follow where it is. Does that make sense? This general effect is called parallax. Okay? So there should be an apparent shift in the position of stars on the sky as the Earth moves around the sun. And the Greeks looked for this. They looked to see if the relative positions of stars moved relative to each other from one time of the year to the next, and they never saw any shift at all. And so for them, this was convincing proof that the Earth, therefore, was not moving. Now, the only way for this observation to be consistent with reality in an Earth that was in a universe where the Earth is moving is if the stars are really, really, really far away compared to the distance that the Earth is moving. Okay? So it's like if you're on a train that's traveling and you look at a distant mountain peak, it looks like that mountain peak is not moving at all. Right? You know what I'm saying? But the reason why it looks like it's not moving is just that it's really far away compared to the distance you're traveling. So if things are closer to you, they shift a lot, and if they're far away from you, they don't shift very much. So the only way that you could have a universe where the Earth is going around the sun is if the stars were, in their opinion, ridiculously far away. It required a universe that was immense. And so at some level, this was dismissed. Because the universe can't be that weird and that grand. Is that clear? So this angle is called the parallax angle. So in astronomy, that's called parallax. And in the end, modern astronomers use such, now we can actually measure these angles. It's very, very hard to measure them. You cannot measure them with your naked eye. You need instruments. But you can measure these angles, and that's one way we try to figure out the distances to stars. And so the largest angle that nearby stars actually do move today is the width of a nickel at 6 miles distance. So that's the kind of angular shift that the stars are moving, that the Greeks were trying to measure. So it's not that surprising they couldn't measure it. Okay? So what that means actually in reality is if this orbit of the Earth around the sun were shrunk down to the size of a nickel, the nearest star would be these bright stars would be 6 miles away. So they're far. Okay? And it was this kind of crazy distance that the Greeks thought, well, that's crazy. That can't be right. The Earth's not moving. So in reality, it's more like that. Okay. Now, there's a problem with Aristotle's picture, and we heard a little bit about this already, in that if you carefully watch the trajectory of, say, Mars over the course of time relative to the background stars, okay, the background stars stay fixed relative to each other, and the planets wander among them. Okay, and the reason for that is that they're closer and they're moving fast, and the stars are far away. We understand that now. But that's what planets means. It means wanderers. So the planets wander across the stars. But what was known is that every now and again, Mars doesn't just keep moving in one direction. It backs up and keeps going again. And so this simple idea that Aristotle had, that Mars just keeps doing this, that can't be right, right? So you would need to do something where it went like this for a while and then randomly backed up and then started going forward again. That's called retrograde motion. Okay, and that retrograde motion was not captured in Aristotle's original picture. But what happened is people tried to develop models that could correct this. Okay, and Ptolemy's model, flash forward to 140 AD, Ptolemy's model was, he modified Aristotle's picture to account for this retrograde motion. And what he did is he created this idea of epicycles. So what's going on is, rather than Mars going around the Earth like this, it's going around in sort of loop-de-loops. Imagine you had a circle, and the center of that circle is orbiting the Earth, and then Mars is orbiting that circle. That creates this kind of loop-de-loop pattern. All right? And so this can, naturally, with air quotations, naturally explain the retrograde motion. This is a movie. I think it's not playing. It's too bad. So what happens is you're looking from the Earth at Mars, and as Mars loops around, it will go forward a little bit, but then start to go backward. And then the projection, it will look like the star goes forward and then backward and then forward again. So anyway, Ptolemy added these loop-de-loops, these epicycles, to make this Earth-centric model of the universe match up with what you basically see in the sky. So it's getting a little funny, okay? You can kind of see now it's getting a little bit gangly, trying to construct a model that works. But that's what Ptolemy did. And the crazy thing, he was basically able to write down a model with lots and lots of loops and stuff. There's a little bit more detail here. I won't really get into it. Where he was kind of jerry-rigged this model that was able to basically predict where the planets were going to be in the sky from month to month and year to year. And the crazy thing is this model of the universe was the accepted picture in the Western world for the next 1,400 years. Now, the model didn't work perfectly. And as astronomical observations got better and better, astronomers did realize that Ptolemy's model had some flaws and couldn't explain everything in perfect detail. A figure of note is this guy Alhazen, around the year 1000, who was this great Islamic scholar. He studied in the House of Wisdom in Baghdad. This is a very famous, Baghdad was a great city of culture and learning, sort of the most important city of scholarship during this time. And he studied there, and many of his writings eventually found their way to medieval Europe. And he was sort of revered in Europe. Scholars in Europe called him the physicist. But one of the things he demonstrated was that Ptolemy's model was not self-consistent. He realized that Ptolemy wanted all these sort of crystalline spheres that the planets were orbiting on, and he realized that they had to kind of crash into each other for it to work. So the model kind of like overlapped and wasn't really working, and he knew that. And what he found and what others found is that they had to keep adding more bells and whistles and all kinds of things to these loops and quadrants and all kinds of stuff to this kind of model where you want to keep the Earth fixed and have the stuff go around it. So people knew, like I say, by about 1000, the year 1000, that something was wrong. And it's unclear, exactly what they were thinking. So I think a lot of these people just said, look, I don't know what's really going on in the real universe, but this model basically allows me to predict where the planets are going to be in the sky, and that's all the king wants me to do. Because then I could do some kind of astrological forecast, right? But it's not clear that they actually believed that this is what the universe was like. So things were beginning to show some cracks. Now, the real turning point in this story comes with Copernicus, who, as I'm sure you all know, is the person responsible, credited with first really pushing this idea in a modern context where the sun is at the center and everything goes around it. Now, Copernicus was a Polish priest, and he was one of the first scholars to have his own library, okay? Because this was after the time of the printing press. So he was able to actually read this literature. He was able to sort of keep track of what was going on with other scholars throughout the world and put together these ideas. And he knew that Ptolemy's predictions were wrong. He knew that Ptolemy was not able to actually predict the positions of the planets in the sky. And moreover, he thought that this model was just ugly. And he thought it would be much prettier and it would be much simpler, okay, and much more divine if the sun was at the center and lighting up the universe. The sun was like a lantern. And all of the planets were illuminated by this lantern at the center. And he published his ideas. Now, I should say that he knew his model that he produced got the retrograde motion right. Okay, and I'll talk to you about this. But basically what's going on is the Earth is going around the sun like this, and Mars is going around the sun like this, and at some point the Earth passes Mars. So it's like, if you're catching up to a runner's going this way, and you pass the runner, it goes forward, and then you start going back again because it's going around the sun, and then it looks like Mars goes forward again. Okay? So it's sort of, because Earth is on the inside track and Mars is on the outside track, they sort of effectively pass each other, and that's what causes this retrograde motion. So you can naturally do retrograde motion, and he could basically do about as well as Ptolemy's model in predicting the positions of the planets in the sky from month to month. But it wasn't, again, it wasn't perfect, and he knew it wasn't perfect. And that's probably one of the reasons why he waited until basically the year he died to publish this idea. Because he worked his whole life to try to make a model that worked better. And he wasn't really able to do it, but he was at least able to put this idea out there. And eventually this idea would lead to a revolution, but it would take some time. Okay? One of the reasons being, of course, is that the data weren't there to support that this model was better than the other one. Okay? a lot of people thought it was crazy. Okay, so Martin Luther called him a fool for reversing the entire science of astronomy for trying to do something like this. So it wasn't like he published it and everyone was like, oh, Copernicus, he's a smart guy. And it wasn't like that at all. So this was my movie that's not going to work, unfortunately. I'll put something like this on the blog or the website, but you get retrograde motion because of this inside-outside track thing. It comes out for free. Now, a really big event in the history of astronomy and our movement towards understanding our place in the universe happened a little time after this. And the date, we actually have a date. You can actually put a flag down and say something very interesting happened on this day. And it was a clear night in November in 1572. And a 25-year-old Dane named Tycho Brahe was taking a walk, I think before dinner one night. And he saw something in the sky that rattled him. Okay? He knew the sky. He was an astronomer, and he knew the constellations like the back of his hand. And he looked up at the sky, and he saw a new star, a star that he had never seen before. Now, this guy is a really interesting figure, by the way. So he's this huge dude, and he had a golden nose. And the reason why he had a golden nose is that he lost his nose in a duel with another guy because they were arguing about who was the best mathematician. So like having a math fight, and he lost the fight. And so like for the rest of his life, he had this metal nose. So anyway, he saw this thing in the sky, and he called his servants over and stuff, and he was like, do you see that? Like, am I seeing things? And they were like, yeah, it's there. And he realized this was important because this means that the heavens can change. Aristotle had said that the heavens are unchanging and perfect. And he saw this new star. Now, he worked quite a long time to convince himself that this was not atmospheric, that it wasn't some kind of light in the atmosphere of the Earth, and that in fact it was beyond the moon. And he was able to do that eventually. And now we know that this new star that he saw in the sky was in fact a supernova. So it was a star actually that had always been there, but it was too far away to see until it exploded as a supernova, and then he saw it. And for a while, it was brighter than Venus in the sky. Now, so here's a picture of that same spot in the sky today, taken in the X-ray. This is a remnant of the supernova that exploded. This is Tycho's supernova today. So for a few days, like I said, the supernova was brighter than Venus. And he showed convincingly that this was not an atmospheric event. He showed that because of the lack of parallax, that is, it wasn't shifting relative to the other stars in the sky from month to month, that it was very far away. So this means that Aristotle's idea that the heavens don't change was flat out wrong. And therefore, maybe all the other stuff that Aristotle was preaching could be wrong. So Tycho becomes a superstar after this. He becomes the most famous astronomer in the world, which at that time I think meant something. And his king, Frederick II, wanted him to stay. Wanted him to stay in the country and not go off to France or something. And so he offered to build him the greatest astronomical observatory in the world. This is part of the story, right? This is actually not a tangent. It's part of the story. And so he did. And it's called the Castle of the Heavens, Raneborg. It's on this island between Denmark and Sweden. You can go there now, and there's a museum and stuff there. And he ruled over this thing like a castle, like he was a governor of it. So he had these sort of army of servants and stuff, and he sort of ran this castle. And he made observations of the heavens with these instruments that he designed. And he was able to compile the most detailed observations of the motions of the planets and the stars that had ever been compiled before. Okay, it was basically he leveraged his celebrity status to make favor with the king. The king built him this nice observatory, and he went to town recording information. There were no telescopes yet, okay? Nobody had a telescope yet, but he devised these instruments that allowed him to sort of measure the angular positions of stars that you could see by eye accurately. Now, around the same time, in fact, when the supernova exploded that Tycho saw and became famous for, there was a young boy who saw that same supernovae, and his name was Johannes Kepler. And Kepler would grow up to be a great mathematician, and a very different kind of guy than Kepler. He was more timid and reserved, whereas Kepler was this big kind of boisterous, kingly figure. But he was enamored with Copernicus's idea that the planets go around the sun. Not so Kepler, by the way. Kepler didn't think that that was what was going on. Sorry, not so Tycho. Tycho didn't think that that was going on, but this younger guy, Kepler, liked this idea. He thought it was aesthetically pleasing, and he was a great mathematician, and he wanted to build a model that self-consistently could put the sun in the center, have the planets go around it, and match all the data that existed. But he realized that in order to do that, he needed the data tables from Tycho. So he inquired about joining him, and Tycho knew that this guy was a mathematical genius and figured he could use him. But he was a little bit nervous that this young whippersnapper, super genius, boy genius guy was going to come and sort of eclipse him. And so he hid most of his data from him. And he said, look, you can have all the data tables on Mars, because Mars was the really hard one. That was the one that did this big, it was hard to explain Mars, and he knew it. He said, oh, I'll give him the hard problem. And he hid all the other data for himself. But it turns out that it didn't matter very much, because Tycho would die within a year, and he died. The story of him dying is crazy. So apparently he went to this with the king. He was invited to some dinner, and he drank all this beer. And he was not allowed to get up from the table before the king got up from the table, and his bladder exploded. Yeah? Right. So it's a crazy story. But anyway, that's what happened. So that just goes to show you, if you go to the king's house, don't drink too much. So Kepler inherits Tycho's data after this and goes to town on it and works really, really hard and is having all this trouble. And finally, he gets a breakthrough. He asks himself, wait, what if the planets don't go around in circles, but they go around in little ovals, little ellipses around the sun? And he found that when he allowed that possibility, everything started to click. So it was a very simple tweak. But once he did this, everything worked. And no one had ever conceived that this shape would work before. Now, an ellipse is actually a well-understood mathematical thing. How many people have studied ellipses in school? Or you remember the word from high school even? Okay. So if you recall, there's a very precise mathematical definition of ellipse. And the idea of an ellipse had been around a really long time. Okay. Now, the Greeks loved circles and spheres. Circle was this perfect thing. But the ancient Greek mathematicians living long, long, long before Kepler had studied this idea of an ellipse because it was sort of beautiful for a number of mathematical reasons. And if you recall, the idea of an ellipse is, there's a couple different definitions of what it is. If you think about it geometrically, you can create a cone and then put a plane through the cone, and the slice of that plane through the cone is an ellipse. Another way that you may remember from grade school is, if you take a string and you tie the ends of the string to two thumbtacks on a piece of paper, and then you trace out that string, it will create an ellipse. And those two thumbtacks are called the foci of the ellipse. So there's very precise mathematical, understanding of what the ellipse is. And it's been around for a long time, thousands and thousands of years. And it was studied by mathematicians basically because of its mathematical beauty, its simplicity, and how it fit in with other ideas in geometry. Of course, the people who first talked about the ellipse, okay, going back to Pythagoras and people like that, They had no idea that it had anything to do with what the planets were doing. The remarkable thing is, that's what the planets do. It turns out this idea of the ellipse that had been around for thousands of years because of its mathematical beauty was somehow fundamentally linked to the way the universe operates, to the way planets orbit around the sun. The sun sits at one of the foci of the ellipse that all the planets go around. That's what Kepler figured out. On top of this, he deduced 3 laws of planetary motion that I'll talk about in the next lecture that more or less described everything that was going on with the planets. One of the ideas was the planets go faster when they're closer to the sun and slower when they're farther away from the sun. Things like that. So at this point, Kepler had constructed a mathematically self-consistent model for the planets orbiting around a sun in the center of the universe. And it works with everything. There's nothing wrong with it. And in fact, it does better than the best Ptolemaic model that exists. But they're still sort of on equal footing. And again, people don't like the idea that the Earth is moving. That's a crazy idea. If the Earth is moving, remember, it means the universe is way bigger than people thought was plausible. So the final nail in the coffin, basically, was driven by this guy, Galileo Galilei. Galileo, in the same year that Kepler published his orbit of Mars, this Italian mathematician named Galileo was working 500 miles to the south, and he had heard whispers that there was this new thing called a telescope. And people would use this telescope to look out and see when ships with stuff to trade were far away and coming in to dock. And so they could have a head start in greeting those ships. They were also useful for, if you wanted to scout out when approaching armies were coming and things like that. But what Galileo realized is, hey, if I could build myself one of these things using lenses, I could point it up at the sky and see what's going on up there. And that's what he did. So he built his own telescope. Turns out the telescope he built was the best one that had ever existed. But it was still only a 10 or 30 power telescope. Okay, this is the kind of telescope that like kids have in their rooms. Like cheap plastic telescopes you buy at like Target is basically this, right? This is what he had. But this telescope, which is modest by today's standards, changed everything. And one of the reasons why it changed everything is, prior to Galileo, every single thing up in the sky that people were studying had been seen thousands and thousands of years before by everybody who had ever lived. Right? So Tycho was studying the same sky that Ptolemy was studying, basically. The same stars, everything. And he might have had slightly better, he had some iron tools and things that he used, but more or less he was still just using his eyes. So everyone was looking at the same data, trying to solve the same problem. What Galileo did is he looked up and he saw stars that no one had ever seen before. He saw new stars. He saw that the moon was very structured, that it had mountains and things on it. And the other thing that he found was that Jupiter, which was thought forever to just be a point of light or possibly a sphere, had moons, and those moons went around it. So it's clear then that not everything is going around the Earth. Jupiter has stuff going around it. So this whole idea of what the heavens were like begins to break down. He was the first person to point his telescope at the Milky Way, this band of stuff, and he showed that the Milky Way was actually composed of new individual stars that no one had seen before. But there's one specific experiment that Galileo did that I'm going to end with. And I like to call this how Galileo killed Ptolemy. So how he put an end to this model. And it's a great example of setting up an experiment, doing the experiment, and seeing which theory is right. Because now, for one of the first times, we have two generally competing theories that are legitimate. Okay. One theory is this theory of Ptolemy and basically Aristotle, that the Earth is at the center and the planets are going around it. a particular planet that Galileo was interested in is Venus. Okay? Now the reason why Venus is interesting in the Ptolemaic model is the circle that it goes around in orbits is always basically tracking where the sun is on its orbit. Remember, the sun's orbiting too. And the basic reason why this is that you may have noticed that the sun is always near, Venus, when you see it in the sky, is always near the sun. It's always pretty close to the sun on the horizon. And the reason why that is, of course, is now we know that Venus is the first planet. So it's near the sun. So when we see it, it's, the sun's always not that far away from it. So it had been known for thousands of years that Venus was always in the sky close to the sun. And so in Ptolemy's model, he had to force the center of Venus's epicycle to be near, to track along with the sun. But what does this mean? This means that the light from the sun is always shining on Venus basically from the side. And it's never fully lighting it up. So what this means is if you can resolve Venus into what it actually looks like, that is, so it no longer looks like a point of light, you would see it looking like a crescent, just like the crescent moon. Okay? So the prediction is that when you look at Venus, if you can resolve what it looks like, it'll always look like a crescent. Is that clear? Is anyone confused by that? Now, in the Copernican type of model, Venus goes around the sun and the Earth is out here. And what does this mean? This means sometimes we view Venus as it's being fully lit up by the sun. So it looks like a full Venus, like a full moon. And when it's over here, it's half lit and it goes through phases. Okay? And when it's positioned this way, it's dark. So the expectation of the Copernican type of model was that you look up in the sky and you see Venus go through all phases, just like the phases of the moon. Whereas in the Ptolemaic model, you don't. Let me just pause here. So first of all, does that make sense? Question with that? Let me just pause here and talk about how specific and detailed this is, okay? And how it was kind of unfair for me to ask you guys the question, all right, convince me just sitting in this room thinking about it for 4 seconds that the Earth goes around the sun. Because it's these kind of detailed arguments that had to be made in order to rule out one model or another. And you could only do this with a telescope, right? If you didn't have a telescope to resolve the details of what the shape of Venus was, it just looks like a point of light, so you're done anyway. You can't begin. So what did Galileo see? Well, he looked, and what he saw was this, right? And that pretty much put an end to this. It's done. So at this point, if you want to explain, it doesn't mean that this is right, but it's consistent with what we see. But it definitely means this is wrong. See what I mean? And so it was this kind of observation, repeated things. So I've given you sort of 6 or 7 things that people began to see to finally convince themselves when they thought about it carefully that the Earth was probably moving and that the planets were going around the sun. Okay. But by accepting these ideas, things changed. So this idea that the sun is at the center had a number of implications, philosophical implications, you could argue. So there's this kind of old thing that a lot of people talk about when they think about the Copernican revolution. You've probably heard about this idea that suddenly we're not the center of the universe, so therefore we're not as important as we thought. I don't know really if that's how much that really matters. That's kind of wishy-washy, I think. It's not clear to me what people really thought of that. But the one thing for sure it implies, in terms of the physical reality of the universe, is that the universe is huge. Way, way, way bigger than anybody thought it was before. And why is that? Why does it imply the universe is big? Help me out. Yes?
We see the stars shifting.
Yes, exactly. So Aristotle said, look, the Earth cannot be moving because if it was moving, we would see the stars shift. Like you're walking through the woods and the trees are shifting. We don't see the stars shift. And the only way that can be true in a model where you're moving around is if the stars are really far away. If that the trees you're looking at in your forest are really far away, and therefore they're all basically in the same place as you walk. Does that make sense? So by accepting a universe that the sun is at the center and the Earth is going around, suddenly the universe becomes bigger. Unimaginably big, really. Okay? It means the distance to the stars are much, much, much farther away than the distances to the planets, which is true. But it makes the universe huge. And it opens up this idea, if you go back to Democritus, maybe this idea that Democritus had is not so crazy. That those stars are other suns. And then around those suns are other planets. And maybe even on those planets there's other life. So it just opens up the possibilities. It just shatters the worldview in a big, big way once you accept this idea. Okay, that's it. Thanks very much.